Okay, Organic Chemistry 2330. Today we're going to introduce Chapter 12. That's aldehydes and ketones. Okay, so the key feature is this is the introduction of the carbonyl group. The carbonyl group is where we have a carbon double bonded to an oxygen. This is the key component in aldehydes and ketones, which will be covered in this chapter, carboxylic acids and carboxylic acid derivatives, which will be covered in the next two chapters, and enolate ions covered in 15. So it's important to learn about the structure and reactivity of the carbonyl compound to allow us to understand the next few chapters. So let's dive into the carbonyl compounds. The first of the carbonyl compounds I'd like to introduce is called the aldehyde. Okay, the aldehyde has a carbon-oxygen double bond, and then to that carbon on there, we have a hydrogen bonded to it. If we have two hydrogens bonded, that's the simplest aldehyde we have, and it's called formaldehyde. And we see right here at the bottom of the page, formaldehyde. Okay, if we have one carbon bonded to the carbonyl and a hydrogen on it, it is still an aldehyde. There's still a hydrogen bonded to the carbonyl, therefore it is still an aldehyde. However, if we have two carbons bonded to the carbonyl, it is now a ketone. So that's the distinguishing factor between aldehydes and ketones is an aldehyde that has at least one hydrogen bonded to it, and the ketones have two carbons bonded to the carbonyl. Okay, so let's talk about the nature of the carbon-oxygen double bond here. The carbon is sp2 hybridized, the oxygen is sp2 hybridized, and they share a sigma bond in that sp2 hybridization. Because it's sp2 hybridized, that means that the carbon and oxygen are both trigonal planar and create a flat plane where the two bonds to other bonds to the carbon are, and the two bonds where the lone pairs of the oxygen are. So if we look at this, we have a nice trigonal planar structure between the carbon and the oxygen here, and the lone pairs stick out in a trigonal planar configuration as well. Now, the remaining p orbital on the carbon here is overlapped with the remaining p orbital on the oxygen here, and they share one electron from each other to create a pi bond. So you have a single sigma bond and a single pi bond in this nice flat trigonal planar structure. Okay, so let's talk about nomenclature first. So in nomenclature, we start with what we usually start with is the longest chain that contains the carbonyl. And if it's an aldehyde, we drop the E at the end and Al. So if it's pentane, but it has an aldehyde on it, you call it pentanal, okay? If it's pentane, but you have a ketone on it, you drop the A and add ONE, and so you have pentanone, okay? So aldehyde is al, ketones are ones, okay? Now, if you have an unsaturation or a double bond in there, you have to signify that you have that double bond. So instead of being propane, it's now propene, and you have to signify that it has that aldehyde on it. So it'd be propenal or propenone. So you would have the E in there to signify the double bond, but you'd still have the Al for an aldehyde or an ONE for the ketone. Now, if you have a cyclic compound like a cyclohexane and you have the aldehyde pendant to it, you have to say cyclohexane plus carbonaldehyde. So you're saying that that's the pendant group to that chain. So let's look at a few examples on this. So on the first one here, we have a four-membered carbon chain. So that gives us butane, okay? Now, because we're naming the parent for the aldehyde, it takes precedent and we start with a number 1 where the aldehyde is. So our substituent on here is going to be in the 1, 2, 3 position, which gives us 3-methyl butanal, okay? Now, just like we said before with the substitution reaction, we have 1, 2, 3 carbons right here, but we have an alkene, so that makes it propene, but it's still an aldehyde, so it's propenal, okay? Now, because the 2 carbon is where the double bond starts, we can signify it as 2-propenal. Okay, so let's use all those rules for this substitution here. We have our longest chain is octane. So but we have 2 double bonds in it. So we have to call it octadiene, okay? But we also have an aldehyde, and that takes the precedence. So that's where number 1 starts. So we have octadienyl. Okay. Now we have substitutions, and because the aldehyde is our number 1 position, we know that our first methyl group is on the 3 carbon and our second methyl group is on the 7 carbon. So we have 3,7-dimethyl, and then our first diene is on the 2 carbon and our second diene is on the 6 carbon. So we have 2,6-octadienyl. Okay. Now, these 2 groups are the same, 7 and 8 are the same, and so that we don't have to say whether it's E or Z, but the 2,3 double bond, we have to say whether it's E or Z, and since this takes precedent on this side, and this has 2 carbons, this only has a single carbon with hydrogens, this takes precedent on this side, which makes it the trans or Ingagen, so we have our 2E, 3,7-dimethyl, 2,6-octadienyl. Okay. So it's much simpler when we're looking at a cyclic hydrocarbon here. We name it for the cyclic hydrocarbon. So in this case, it's cyclopentane. And then we add carbaldehyde. So we have cyclopentane carbaldehyde. Okay. So in the case here, we have cyclohexane. And since the carbonaldehyde is defining it as our parent name, that's where our 1 position starts. So our substitution's on the 1, 2, 3, 4 position. And the hydroxide is up and the aldehyde is down based on the wedge structures. So we have trans 4-hydroxy cyclohexane carbonaldehyde. Okay. Ketones are a little bit easier. You take the main name and then you put the position on where the acid, the ketone is. So for example, right here, this would be 2-propanone because the carboxylic, the carbonyl group is in the 2 position. Here we'd have 1,3-dihydroxy propanone, or the common name for this compound would be dihydroxyacetone. Okay, let's use that nomenclature again for the next ketone down here. We have 1, 2, 3, 4, 5, 6 carbons in our main chain, and we want to put the carbonyl at the lowest number. So we're going to number from this side here. So that's going to be our 1, 2, and 3 position right here. So we have hexane, but we have a ketone, so it's hexanone, and that carbonyl is on the 3 position, so it's 3-hexanone. Okay, and that leaves us 4 and 5, so we have a methyl substituent on the 5 position, so it's 5-methyl 3-hexanone. Okay, now just like with the aldehydes, we have to talk about our cyclic compounds. If the carbonyl is part of the ring, we just have to call it cyclohexanone because it's inside the ring. And so we again start numbering from the cyclohexanone, from the carbonyl. So this gives us our 2 positions. So it's 2-methyl cyclohexanone. As we get to other things like the 2 compounds here, we actually have common names for them. So if we can think of this as like acetic acid here, so it's acetophenone because this is the phenyl ring. Or here we have 2 benzene rings and a ketone, so it's called benzophenone. And those are common names, and those are commonly used in our nomenclature as well. Okay, now we've introduced a number of functional groups so far. We started with the alkanes, the alkenes, the alkynes, and then we had alcohols. And so alcohol started to take precedent over the alkenes and alkanes and alkynes. And so now we have to have a hierarchy of naming structure. So we have alkanes, alkenes, alkynes, and then alcohols. And other things like amino groups, halides, and thiols are all substituents below those. Once we get to alcohol, though, the next thing above alcohol is ketones. So if you have an alcohol and a ketone on the same compound, it's named for the ketone, and therefore you have hydroxy ketone of some sort. Aldehydes are above ketones on our naming structure, so that if we have an aldehyde and a ketone, it's named for the aldehyde, okay? So for example, in this case here, we have a 4-carbon chain. In this case here, we have a 4-carbon chain, so it's butanal, but we have a ketone on our 3 position here, so we call that 3-oxo. The oxo is indicating we have a ketone, but the aldehyde takes precedent over ketones, so it's named for that, okay? The only thing higher than aldehyde is the carboxylic acid. So if you have something that has a carboxylic acid on it, it is the #1 priority. If there's one there, that's what you name it for, and all the other substituents are named below that. Okay, so just like ketones, which have the oxo substituent here, the prefix, aldehydes also have the oxo, but you still have to signify which carbon it's on. Okay, we'll get into the naming of carboxylic acids when we go to that chapter. However, I want you to see that there's a priority as we move up to more and more functionalized groups. We have to name them for the higher order. So we have alkanes, alkenes, alkynes, alcohols, ketones, aldehydes, and our highest group is the carboxylic acid. Okay, so because these are so common and used in the industry a lot, there's a lot of common names associated from that. And typically they're named for the carboxylic acid. So for example, our simplest aldehyde here is the carbonyl with 2 hydrogens on it. It's called formaldehyde. You may be familiar with this. It's actually a carcinogen used in a lot of glues and stuff. So it's used only in industrial conditions now, but it can be used safely in that way. If we take that formaldehyde and oxidize it to the carboxylic acid, we end up with what we call formic acid. So we have the carboxylic acid function here, which we'll learn about in the next chapter, and we have the aldehyde form. Now, if we have acetic acid and we convert that to the aldehyde, we have acid aldehyde because it's based on the acetic acid system here. There's also some common names for ketones we have. One of them is called MEK. And when we talk about common names of ketones, you typically name one alkyl group on one side of the carbonyl and one alkyl group on the other side of the carbonyl, and then put the word ketone at the end. So in this case, we have methyl, ethyl, ketone. Notice it's not in alphabetical order. Common names do not follow the alphabetical order rule. In this case here, we have diethyl ketone, because we have 2 and they're the same. And in here we have dicyclohexyl ketone because we have a cyclohexyl group on either side of that carbonyl group. Okay, so let's talk about some physical properties and what makes the carbonyl group a functional group. Okay, unlike an alcohol where we have an acidic proton, we do not have that. We have a polar carbonyl group. And it's polar because the oxygen is more electronegative than carbon, meaning it's pulling electron density away from the carbon, making the carbon partially positive and the oxygen partially negative. This is the reactivity we're looking for in our carbonyl systems, okay? Now, if we were to draw a resonance hybrid structure, we would actually have a positive charge on the carbon and a negative charge on this oxygen here. And that leads to its reactivity. So we want to think about the carbonyl as having that partial resonance structure, giving us what we call a partially positive carbon on one side and the partially negative oxygen on the other. Okay. Because we have this permanent polarization of that bond, we actually end up with a dipole-dipole interaction when it dissolves in solvents. So the dipole-dipole interaction is better than the nonpolar interactions we find. However, it's not as strong as the hydrogen bonding we see in alcohols. So that affects our boiling points if we look at the different functional groups. So let's look at a comparative table here. Now, if we find some compounds that are all about the same molecular weight, so we're really not worried about the molecular weight, all we're looking at is the molecular interactions that change their boiling points. If we look at ethers, we have a little bit of a polar bond there because it's bent right here, and we have a boiling point that's fairly low, around 34. If we look at the hydrocarbon, which has almost no polarity to it, it's about the same, of having a boiling point of around 35, 36. Just by adding the carbonyl in the form of an aldehyde here, we almost double the boiling point because we have that polarized bond here of the carbonyl giving us our dipole interaction right here. And so it can dipole and interact with another one next to it here, so that that interaction, that dipole-dipole interaction, is giving it that increased boiling point. So we see the same increase when we have ketones. where they have that dipole-dipole interaction to create a higher boiling point. Now, once we go to an alcohol here, now we have hydrogen bonding and the boiling point jumps again. So hydrogen bonding is stronger than our dipole-dipole interaction, but our dipole-dipole interaction is stronger than our regular just van der Waals interaction. Now, once we go up to the carboxylic acid's hydrogen bond very strongly, and we see another jump in boiling point based on that hydrogen bonding. Okay. Because of this hydrogen bonding and the fact that it doesn't hydrogen bond, but it does have a dipole interaction, it can interact with water. Therefore, very small aldehydes and ketones are very soluble in water because they can form what's called a hydrate. We're basically adding water across that carbon-oxygen double bond to create a structure that looks something like this right here. Okay, so this is a reversible reaction. Well, which way it shifts depends on how stable the material is. Okay, but as your chain gets longer and longer, as it gets more nonpolar, it becomes less and less soluble in water. So the carbonyl can only pull so many carbons into solution. After a while, the carbon chain just gets too long and it becomes almost insoluble. So for example, right here in the hexanal, we are barely soluble in water, where the propanal was fairly soluble in the ethyl. So when we go from 2 carbons, which is completely soluble in water, to 6 carbons, it only barely goes in, if at all. Okay, so that carbonyl is giving us the functionality of that dipole interaction. It's also giving us ability to bond with water to reversibly to give us that hydrate, to give us water solubility. And stay tuned for the next video on some of the reactivity of the system.